So next is stress and strain theorems. So basically stress and strain have the same definitions, like stress is force per unit area and strain is the change in length by original length, or the change in volume over original volume, or the change in angle over the original angle, or we can say strain means the ratio of the change in shape to the original shape. Now when we speak theorems, it means that how exactly the changes are taking place. One is called the transverse variations and other are called the longitudinal variations. So when we apply some force, it is necessary to understand whether the force applied is perpendicular to the plane or it is applied that is horizontal to the plane. So this way we will use the two terms longitudinal and transverse. Transverse is basically related to perpendicular direction. So theorem on the stress and strain we have to go through. So now we come towards the main concept, that is every tensile or extension force increases the length in its own direction and contraction in the perpendicular direction. Every compression or contraction force produces a contraction in its own direction and elongation in the perpendicular direction. Elongation means the change in length. Shearing strain is equivalent to the sum of elongation and the compressional strain in the direction perpendicular to each other. This is one of the theorem on the strain. And earlier that there was this theorem on the stress, that is the compression. When we speak compression, it means something is coming close. Shearing stress is equivalent to the sum of tensile stress and compressional stress. So if we add tensile stress and compressional stress, it becomes the shearing stress in directions perpendicular to each other. Now we have to go through with the relation between y, k, neta and sigma. Sigma stands for Poisson's ratio, neta stands for modulus of rigidity, k stands for bulk modulus, and y stands for, that is, coefficient of Young's modulus. So y is given by formula, that is 3k into 1 minus 2 sigma. It is not necessary to write these formulas, rather we have to remember them for the solution of the numerical problems. Now second formula is that the Young's modulus is twice the modulus of rigidity into 1 plus Poisson's ratio. Poisson's ratio will be beta over alpha. Beta is the transverse strain and alpha will be the longitudinal strain. And strain means the change in shape to the original shape. The third formula will be Poisson's ratio can be given by composition 3 times the bulk modulus of velocity minus twice the modulus of rigidity divided by 6 times the bulk modulus of velocity plus 2 times the coefficient of rigidity. And in the fourth formula, the Young's modulus of velocity will be 9 times k neta, where k stands for bulk modulus of velocity, neta stands for the coefficient of rigidity divided by coefficient of rigidity plus 3 times the coefficient of bulk modulus of elasticity. When we use this term bulk modulus, we are referring to liquids as well as gases, because gases are also fluids. Now the fifth formula is, that is the Poisson's ratio. So Poisson's ratio have different formulas which we can work out, but it is not necessary at this stage. We can simply remember the formula to solve the numerical problems. The Poisson's ratio is given by y divided by 2 times the modulus of rigidity minus 1. And the sixth formula will be 9 over Young's modulus is equal to 3 over coefficient of rigidity or the modulus of rigidity plus 1 over that is bulk modulus of elasticity. Now we will come towards the work done in stretching a wire and elastic potential energy. So first of all, work done has the same definition as we have discussed in work, power and energy. Work done is basically the product of force and displacement. Now here we are taking a wire and that wire is to be stretched. To stretch that particular wire, we have to suspend some load on that particular wire. The load will make the wire to be stretched, and when we remove that load, the wire will come back to its original position. These facts we have to discuss. So work done is force multiplied by distance. Force will be the weight suspended on the wire, that is mg, and the length will be taken as dl, or change in length will be small l, and the elastic potential energy, that is potential energy within the elastic limits. Elastic limits that we have not to come towards the break point or the yield point. So within the elastic limit, we have to go through the potential energy. That is, potential energy is the work done to maintain the position or condition of the body. Now we come to the main concept. When a wire is stretched, obviously wire can be stretched by loading it. Work is done against the interatomic forces. Now here we are using a term, interatomic forces. There is wire is made up of atoms, and atoms are arranged in a wire in three-dimensional repeated pattern. The axes on which the atoms are arranged are called the lattices, and the distance between the two atoms is called the interatomic distance, and the force between the two atoms on the lattices will be known as interatomic force. So normally, up to the time we don't disturb the position of the wire, the interatomic forces remain the constant. But when we do work or when we apply force on the wire, we find that distance among the atoms in the wire begins to increase. So distance increases and force will be the weight. So that is mg multiplied by L, and that mg multiplied by L is stored in the wire in the form of elastic potential energy. So I am repeating it. When a wire is stretched, work is done against the interatomic forces, which is stored in the form of elastic potential energy. So it is shown in the figure. The very first figure towards the light, that is unstretched length, that is the original length of the spring. The second one is that a pink portion is indicated. The pink portion is the load suspended. So increase in length, that is taken as L. Then in the third figure towards the right, the same load is there, but the load has been increased, and the increase in length is, that is 2L. So earlier it was unstretched, then we have stretched it by suspending the load. The length increases L, and then we have changed the load. It is double. We have made double of it, and then we will find that it is stretched to L. Work done is obviously given by the force and increase in length. So we have to take the average force. Obviously, if force is F, the average force will be half of F, that is F over 2. And during stretching, the change in length will be L. Therefore, work done during this process is half F into L. And this half F into L is stored in the wire in the form of that is elastic potential energy. So work done in stretching a wire is given by function half F into L, where half F is the average force. Now, this work done is equal to stored elastic potential energy represented by U. So U is given by W, that is W and U are numerically the same. U is, that is the stored elastic potential energy, and W is the work done which has been stored. So it is given by half F multiplied by L. The area of cross section of the wire is A, and its initial length is L. So if A and L are multiplied, that becomes the volume. So potential energy will be half F over A. Force by area means pressure, that is half pressure into strain multiplied by LA, original length into original area, and that gives the volume. So now the theorem will become half stress into strain into the volume of wire, because area of cross section into length gives the volume of the wire. Stored elastic potential energy per unit volume of the wire, that is designated by small g. So that is given by half of stress multiplied by strain. Stress means it is force by area, and stress will be change in length over original length. Wherever we will multiply area and length, that will become volume, and stress will be force over area. Now, this can be written as half of Young's modulus of velocity multiplied by stress into strain, or half into strain. Like if we will take y as stress over strain, then one of the strain will cancel off, and the remaining value will become, that is, half y strain into strain and half y into strain square. And if we wanted to come to the previous line, y can be taken as stress over strain. One of the strain will cancel off, and we will again come to the original part, that is half y into strain into strain.